This video presents our work towards investigating the functional advantages of bio-inspired materials via simulated robotic hopping. In this work, we developed a novel method for modeling and simulating physical materials and investigating how bio-inspired material relationships can augment robotic locomotion. Our approach models links as a collection of linear springs embedded into fixed volume cylinders. These springs and links can be customized across known materials and approximate a one-dimensional Elastica model. To evaluate the computational requirements of material inclusion, we systematically evaluated the required simulation time step across 400 unique density moduli combinations. We find that time step scales log linearly with both material density and modulus. In other words, more porous materials or materials with a higher modulus require slower simulation speeds. To test our hypothesis that physical materials influence functional advantages, we leverage our modeling technique to simulate a range of materials across 4 different hopping behaviors, including static hopping, forward hopping, ramp hopping, and circular hopping. We selected common performance metrics to allow comparison between materials, which includes average power consumption, tracking error, and jerk. Our results find that material inclusion significantly reduces tracking error, with heavier materials like stainless steel decreasing tracking error by 55% across all behaviors compared to the Majoko default. However, these material benefits are offset by requiring increased power to achieve the same hop height. By isolating changes to material density versus modulus separately, our results also find that material density influences tracking error, while material moduli influences jerk. Finally, we leverage our technique to study the benefits of a combination of materials or material gradients. These material shifts are commonly found in biological systems, such as in tendon muscle connections, and allow functional advantages but have yet to be widely adopted in fabricated materials for robotics. When we compare the Majoko default to stainless steel, we see increased power consumption and decreased tracking error. However, when we make a functional gradient between 3 materials with increasing moduli from PVC to Titan to stainless steel, we counteract the negative trade-offs. Our results indicate that biological functional gradients cancel the negative trade-offs of material inclusion, allow simultaneous minimization of tracking error and power. Furthermore, functional gradients can also decrease the jerk experience for hopping to the same height depending on the direction of the material grading. The key takeaways from this work is that inherent complexities of materials drive functional improvement in robotics. Thank you for your attention.